But if we now have a way to represent all inputs in the world, be it letters, numbers, images, videos, anything else, and get output from some problem-solving process, like how do we actually solve problems? Well, the secret sauce in the middle here is another term that you've probably heard in the real world nowadays, which is that of algorithm, step-by-step instructions for solving some problem. So this ultimately is what computer science really is about too, is not just representing information, but somehow processing it, doing something interesting with it to actually solve the problem that you've been provided as input so you can output the correct answer. Now, there's all sorts of algorithms implemented in our phones and in our Macs and PCs, and that's all software is. It's an implementation in code, be it C++ or Java or anything else, other languages exist too, in code that the computer understands, but it's still just step-by-step instructions. And among the things we'll learn in CS50 is how to express yourself in different ways to solve problems, not only in different languages, but using different methodologies as well. Because as we'll see, among the reasons we introduce these several languages is you don't just learn more and more languages that allow you to solve the same problems. Different languages will allow you to solve different problems and even save you time by being better tools for the job. So here, for instance, on an iPhone is maybe a bunch of contacts, which is presumably familiar, where we might have a whole bunch of friends and family and whatnot, alphabetized by first name or last name. And suppose we want to find one such person like John Harvard, whose number here might be +1 949 468 2750. Feel free to call or text him sometime. This is the goal of this problem. If we have our contacts app and I start typing in John's name by first name or last name, the autocomplete nowadays kicks in and it somehow filters the list down from my 10 friends or 100 friends or 1,000 friends into just the single directory entry that matches. So here too, back in the days of RG&B projector, we had phone books like this here too. I'm pleased to say, thanks to our friend Alexis, this is the largest phone book that we've used for this demonstration. This is an old school phone book that's essentially the same thing as our contacts app or address book nowadays, whereby I've got a whole bunch of names and numbers alphabetically sorted by first name or last name, whatever, and corresponding to each of those is a number. So back in the day, and frankly, even nowadays in your phones, how do you go about finding someone in a phone book or your contacts app? Well, you could very naively just start at the beginning and look down and just turn one page at a time, looking for John Harvard in this case. Now, so long as I'm paying attention, this step-by-step process will get me to John Harvard. Like, this is a correct algorithm, even though you might kind of object to how I'm doing this. Why? Like, what's bad about this algorithm? It's just slow. I mean, this is crazy slow. If there's like 1,000 pages in this phone book, which looks like there are, like this could take me as many as 1,000 pages, or maybe he's roughly in the middle, so like 500 pages. Like, that's crazy. That's really rather slow, especially if I'm going to do this again and again. Well, what if I do it a little smarter? Grade school, I sort of learned how to count 2 at a time. So 2, 4, 6, 8, 10, 12, 14, 16, 18. Again, if I'm paying attention, I'll get there twice as fast because I'm counting 2 at a time. But is that algorithm step by step correct? And I'm seeing no, but why? I might skip over John Harvard. So just by bad luck and kind of with 50-50 probability, he's going to be sandwiched between 2 of the pages. Now, I don't have to abort this algorithm altogether. I could just, as soon as I get past the J section, if we're doing it by first name, I could just double back 1 page and just make sure that I haven't missed him. So it's recoverable. And this algorithm, therefore, is sort of twice as fast, plus 1 extra step maybe to double back. But that's arguably otherwise a bug or a mistake in the algorithm if I don't fix it intelligently. But what did we do back in the day? And what does your iPhone or Android phone do? What they typically do is they go roughly to the middle, look physically or virtually down. They see, oh, I'm in the M section. And so which side is John Harvard to the left or to the right? So he's to the left. So I could literally now, Jesus Christ. We talked about this before class, that this might be more, oh my God. There we go. We can tear the problem in half. Thank you. It's been a while. We can tear the problem in half. We know that John Harvard is to the left, so I can throw half of the problem away if dramatically, such that I'm now gone from a 1,000-page problem to 500 pages instead. What now can I do? I can go roughly to the middle here, and maybe I'm in the E section. So I went a little too far back to the left, but I kept it simple, and I just divided so that I can conquer this problem, if you will. And if I'm in the E section now, is John Harvard to the left or to the right? To the right, so I can again, Jesus Christ. Tear the problem in half. And now, thank you. So now John Harvard, again, is going to be in this half. I can throw this half away. So now I've gone from 1,000 to 500 to 250, and I can repeat down to 125, half of that, half of that, half of that, until I'm left with, finally, just a single page. And John Harvard is hopefully now on this page, such that I can call him, or not at all, at which point this is all sort of for naught. But what's powerful about each of those algorithms is that they're sort of good, better, and best. Like they all get the job done, conditional on the second one having that little fix, just to make sure I don't miss John Harvard between two pages. But they're fundamentally different in their efficiency and the quality of their design. And this is really representative of one of the emphases of a class like this. It's not just about writing correct code or getting the job done, but doing it well and doing it quickly, using the least amount of CPU or computing resources, using the minimal amount of RAM, using the fewest number of people, using the least amount of money. Whatever your constrained resource is, solving a problem better. So that first algorithm, step-by-step instructions, was all about doing something like this, whereby the first algorithm, if we plot things on a grid like this, we have on the x-axis a representation of the size of the problem. So this would mean small problem, like 0 pages. This would mean big problem, like 1,000 pages. And on the y or vertical axis, we have some measurement of time. So this is the number of seconds or the number of page turns, whatever your metric actually is. So this would be not much time at all, so fast. This would be a lot of time, so slow. So what's the relationship if we just roughly draw these three algorithms? Well, the first one is technically a straight line. And we'll describe that as n. The slope is n, because if you think of n as a number for the number of pages, well, there's a one-to-one relationship in the first algorithm as to how many times I have to turn the page based on how many pages there actually is. And you can think about this in the extreme. If I was looking for someone whose name started with Z, I might have to go through like 1,000 darn pages to get to that person whose name started with Z, unless, again, I do something hackish and just kind of cheat and go to the end. If we execute these algorithms again and again the same way, that's going to be pretty slow. But the second algorithm was pretty much twice as fast, plus that one extra step potentially, but it's still a straight line. Because if there's 1,000 pages, and I'm dividing the problem, I'm doing 2 pages at a time, well, that's like n divided by 2 steps, plus 1, give or take. But it's still a straight line but it's still better. Notice, if this is the size of the problem, 1,000 pages for instance, we'll notice that the first algorithm took literally twice as much time as the second algorithm. So we're doing better already. But the third algorithm, fundamentally, it's going to look something like this. And if you remember your logarithm, so to speak, sort of the opposite of an exponential, this curve is so much lower and flatter, if you will, than either of these two. Mathematically, more on this another time, the slope is going to be like log base 2 of n, or just logarithmic in nature. But what it means is that it's growing very, very, very slowly. It's still going up. It's never going to flatline and go perfectly horizontal, but it goes up very slowly. Why? Well, if you think about two towns nearby, like Cambridge on this side of the river and the town of Alston on the other, suppose that they still have phone books like this one, and they merge their phone books for whatever reason. So overnight, we go from a 1,000-page phone book to a 2,000-page phone book. The first algorithm is going to take literally twice as long, as will the second one, because we're only going through it 1 or 2 pages at a time. But if the phone book size doubles from this year, for instance, to next year, you can kind of, in your mind's eye, think about the green line. It's not going to go up that much higher. Why? Well, practically speaking, even if the phone book becomes 2,000 pages long, well, how many more times do you have to tear or divide that problem in half? Just one, because you're taking a 1,000-page bite out of it, or 500, then a 250. You're taking much bigger bites out of it than just 1 or 2 at a time. And so what computer science and what algorithms and about good design is about is figuring out what is the logic via which you can solve problems not only correctly, but efficiently as well. And that then gives us these things called algorithms. And when it comes time to code, which we're about to do too, code is just